tutorial where we are going to show you how to use a TV studio and the data that you already obtain via some using some DFT packages to create a tight binding Hamiltonian. So in this tutorial we are using TB Studio version 1.3.2 and we are going to use the examples that you can find on the website. So we already download them here in this folder. And for start, we are going to show you how to create a graphene two-band Hamiltonian, tight binding Hamiltonian, using data that was obtained via OpenMX. So let's go inside the folder. And here I'm going to show you how these bands look like. So here you can see how it looks like, how they look like. So we have S and P orbitals. So S orbitals shown here. And of course, for the graphene, the most important are the PZ orbitals, the blue one here. And those are the orbitals that actually we are going to use to create a tight binding Hamiltonian for graphene. Okay, so let's start TB Studio. So in the folder with the example, you have the file info.txt where you can find the data for the optimized graphene unit cell. So we will now start by inserting this data into the TB Studio. So let me copy this. So let's put it here. So you can already see here how the unit vectors are changing. And for the y coordinate, let's do the same. And yeah, so of course graphene is two-dimensional, so for the third vector we can put whatever we want. And now you will need to insert also the fractional coordinates. So let's do one by one. So here, copy them and paste here. And now for the kind, we will put 6, which is the atomic number for graphene, for carbon, sorry. And you can see now how the atoms appear within the unit cell. Let's now go to the tab structure. Here you can play with the size of the tight binding Hamiltonian that you want to create. If you click here, show tight binding model, you can see how the unit cell looks like and together with the neighbors, with its neighbors. So here we added one unit cell in both directions of the of our tight binding model. If you change it to 2, now you can see how the unit cell looks like together with its neighboring unit cells, 2 neighboring unit cells in each direction. However, since we are using a simple graphene without any complex interactions, just one neighboring unit cell in each direction will be sufficient for our model. Now let's define the orbitals for each of the atoms in our model. So as I told you, we are going just to use PZ orbital for graphene. So let's name it CPZ. And now you click add TB atom type. So below you can see so here we click add shell, and now you can see all the different orbitals. So we only leave PZ. Okay, like this, and let's scroll down, and now you have to define for each atom within the model this type of orbital. Next step is to define bonds in our tight binding system, and so we click to this bonds tab. So here you can manually select bonds between different atoms. To do so, you click on one atom and then hold the control and click the other atom that you want to form the bond in between. If you did it correctly, the tab here, pick the selected pair of atoms, will be green. You click on it and click set bond. So now you can see that the bond is created between these two atom types, and here you can see how that additional bonds are added between the atoms of the same type. So we do the same for the other atoms, and we connect them all. Now that we are defined our structure, we go to setup. Now we want to load the data obtained from the OpenMX. So we click Open File and we search for the file from the output from the DFT. Okay, so here we select it, and you can see on the right the DFT band structure for Graphene 2 band model. So here, as I already told you, because we are interested in the low energy spectrum, we are going to fit our data to the PZ orbitals, so the ones that are closest to the Fermi energy. Choose the bands that we want to fit to the DFT data. So because we have a 2-atom Hamiltonian unit cell, actually we will have only 2 tight binding bands. So in this field, tight binding bands range, we will write 1, 2. In case if we had, for example, 10 bands and we wanted to fit first 5 bands to the DFT data, then here we would write 1 to 5. However, since we have only 2, we want to fit both of them to the DFT data. And in the field DFT first band, we are going to write the number of the first band from the DFT that we want to fit to our tight binding data. So here this is the 4th band, 1, 2, 3, 4th band. So our fitting starts from this band. So now we are all set. So let's go to SK tab. Here we are going to define the independent parameters for the Slater-Coster matrix and the on-site energies. So we click first on evaluate independent parameters. So since the Fermi energy is at 0, we don't need to change the on-site energies anymore. I mean, we will leave 0. And the only parameter that we need to change is this pp pi parameter. So let's start with the guessing value of -4. You can already see now how the bands change according to that parameter that we set. And now we can start with our fitting. Click on Analyze and start. Okay, we get a warning here. It tells us that the unit vectors of our tight binding model and the DFT model are not the same, because we put for the C vector 5 instead of 20, which was in DFT, but you can ignore this message. This bottom window, you can see the fitted structure, how it looks like. You can see that actually it's not well fitted to the DFT structure, and that's because we are using the whole band. So to get more accurate data, we will just select the 2 bands around the K point. And to do that, we are using the tool called brush, shown here. So now I can select So here now I can select the part of the band that I want to use for fitting, and I will just use this part around the K point. Okay, let's start our fitting again. now here in the terminal we got a message that the convergence is achieved, and if you check for the last value of the pp orbital, we get the famous value for graphene minus 2.2. If you want to get a better fit for the tight binding, for this tight binding we need to include more orbitals, but that will be discussed in the next tutorial.